All right. So let me see. Who knows what's in the hearts of men? Who knows if I say parametric equations, what does that mean? It doesn't mean you have two metric equations.
What does it mean?
What means you have a sad day?
Parametric means you have a sad day?
Parametric is when something is based on time. Yeah?
Possibly.
Or there's a parameter to it.
There you go. So the example I'd like to give is actually something from statistics, because this is sort of the idea. And I just went over this in my 176 class. Of course, we're going to do calculus on this bad boy, so we'll take it a little bit to the next level. But the basic idea of parameter is, believe it or not, related to this. Say I have a shop where I sell ice cream. And next door to me, since I say the word water, weird, come to find out, I'm going to say H2O. So next door to me is this guy that sells some high-quality H2O. Right? And I've noticed that whenever he sells more water, more H2O, somebody finally explained to me, I put an R in there, and there were water, and that's just the way I was brought up.
Water.
Yeah, water, excuse me. My next door neighbor sells water. So he sells water, and I've noticed when he sells more H2O, I sell more ice cream. I'm thinking, holy crap, so the water, H2O, makes people want to eat my ice cream. Holy crap, all right, good. So I want to advertise that amazing H2O, right? So you guys kind of with me now, of course,
Yeah.
nobody's looking at me like I'm crazy. What's the real story?
Because
Because it's probably getting hotter, and that's why they're going to, of course, they're going to get H2O, and they're probably going to get some ice cream, right? So there's a third behind-the-scenes thing. There seemed to be a relationship between my ice cream sales and his H2O sales, but these really didn't affect each other. They were both affected by a parameter. So a parameter is sort of a variable that's behind the scenes. Parameter means different things in different situations. And you can have more than one parameter, actually. But we're going to start with just one. So what does this really mean? So, for example, I like Etch-a-Sketch. If you had an Etch-a-Sketch and you had one person on one knob and the other person on the other knob, and this guy's going slow, it's going fast, you're basically making a graph of an equation, sort of. But how quickly you turn the knob defines how quickly the x variable is changing or how quickly the y variable is changing, depending which knob you're changing. Are you guys kind of with me? So normally, the way we've looked at an equation like this is we've said when x is 1, y is 1. When x is 1, blah, blah, blah. Right? So x was kind of controlling the y. And then you move a little bit ahead and you're like, it doesn't really matter which one you look at as controlling, but one of them is controlling the other one. Meaning it's an independent variable. You can put stuff in for it. Are you guys still with me? So now parameters say, screw all that. Everybody's being controlled. All right, now we get into the conspiracy theory. Mel Gibson. Reference? No reference? Well, thank you. Right. Where we have a situation like this. Oh, you can do it, Jeff. I don't know if I can do it. Sure, I like it. So if I want to graph this, I'm still going to graph it on an xy plane. There is no t-axis. T is behind the scenes. T is controlling what the x piece and the y piece of my points are. So the really cool thing with this, and the same thing happens with polar graphs, is we can get graphs that look very much like spirograph graphs. If I say the word spirograph, is anybody with me?
That's the thing. Like,
they have like a big gear and a little gear, and you put your pen in and you move it around, and it makes shapes like woohoo, yeehaw. Yeah. So we're going to see what the equation of those shapes are.
There's an equation? I thought there was just a 3-year-old.
Dude, there's a little 3-year-old with a pencil and gears and paper, and then we're like, there's an equation. And then you're like, math screws everything up. No, come on. Math is awesome. Math says there happens to be an equation for this. Of course there is, because there's a relationship between the gear size and where you put the pen and all that. So if there's relationships, there must be an equation governing that reflects those relationships. Yes, sir.
Where would a graph like that apply in like real life?
So, for example, do you remember that, or did you hear about the lander that I forget?
The comet?
Europe, I think, is the ones who did this. Maybe I'm wrong. I can't remember now. They sent it and it landed on the comet. Did you guys hear about that?
Yeah, it was like.
If you didn't, look that bad boy up. It's some cool shit. And the equations, which relates to the commands you give to the little dude, the lander, the equations relate to the commands you give to it, are parametric equations as far as its orbit goes, right? So the shape it would create if you allowed it to continue its orbit out would be some kind of spirally thing. Now, of course, at some point it intercepts the thing and it stops. So it's like the 3-year-old kind of like getting bored. So, but we landed on the thing, so we stopped, of course, right? You guys kind of with me? I mean, parametric equations are stupid awesome because they give you so much more control over x and y. Before, you had to pick one of them and then control the other. Now I can control both of them. I still have points in 2 space. There's still points. But now I can do these funky-ass things. It's awesome. And then the idea of parameter goes further. How many of you guys have to maybe take linear algebra?
I think so.
Several of you. Awesome. Many of you. Kick ass. That's so awesome. Your parameters are going to rule you for a little while in that class. Or you will rule them, hopefully. Trust me on this. All right, that's enough of that. So let me ask you this: how would I graph this thing? So I'm going to graph it on an XY plane. What would my table look like to help me graph this?
You make an X and a Y T-chart.
Sure. So T, X,
That's what. Yeah. That's what
Y.
And then just plug in.
He's behind the scenes. He creates each of these points, and then we plot those points, right? So do that. Do that for this.
Our equations.
And I'll tell you this. Say again. There's your equations.
Starting with the 0.
Here's your, let me say that. So let's do from, what you got, Jeff? Let's do from negative to 2. Sure. We'll just do that little piece of it.
And she uses this a lot for physics also.
You can. Polar, parametric, when you get to Math 281, spherical coordinate systems, cylindrical coordinate systems, they're just different coordinate systems that make problems possibly easier to do if you switch them to those coordinates. So physics, there's a lot of, and how many guys have taken physics? Anybody? So in physics, you have those problems where they say you shoot it at 38-degree angle. How far will it go? So your x and your y are both kind of controlled by theta. So theta is sort of the parameter there. You guys you've already kind of done this. You just don't have to say that. You don't actually have to write it as a parametric system of equations, but you could.
Right.
So it's an option that you can use. Sometimes problems are impossible to do unless they're in a certain system. Other times you can choose whatever system you want to, and some of them are easier, some of them are harder. Does that make some kind of sense? So the more options we have, the better. So here's an option for several things.
You want us to graph it too?
Yep, sorry. Shouldn't be too hard. What you got? All right.
4101.
Is it 4? Yeah.
4101.
0 is 1.
0.
1 is 0. 2 is 4, so it's 1 again, right? So that's where that parabola turns. This is a very simple example of parametric equations.
So this is going to be the final?
So see on the y, yes, definitely. It's going to be on the next test. All right, so then I got 3, 9, 2, 4, 1, 1, 0, 0, negative 1, 1. So that's for this range. And now, of course, what shape is that? Yeah, parabola. And actually, I should just stop. Good old, I went too far, didn't I? Did I go too far? No, I didn't. I'm fine. Huh?
It's the other way around.
What's the other way around?
It's negative 2 and then minus.
Say again? Sorry?
It's negative 2 and then
No. This is t.
minus.
So what am I plotting? There's my points to plot, right? You guys see that? So t controls the points. T has no axis, so it doesn't get to show up. But it's the behind-the-scenes player. It doesn't want to show up, right? It's like the kingpin. Until the end of that. And then he wanted to show up, and anyway, if you're not watching it, then you have no idea what I'm talking about. There you go, yes. Thank you.
That new show, the
Huh? Yeah, not the Ben Affleck, whatever the hell it was.
He's Batman now, so it's okay.
Sure, yeah, that's fine. Let's destroy something else. Can you guys, now, is that cool by itself? Was that hard? The only way it would be a little bit harder is if I had to get more resolution. If I had a function that was moving very quickly, I might have to do the halfway points. Or, if I have a trig function, I'm going to have to be careful about my inputs. You guys kind of with me on that? All right, so trig functions become a huge part of this parametric problem because they give me that ability to make circles and stuff and stuff. All right. Now, the next level of thing I could do with this is, can you write what rectangular coordinate system equation this represents? And we already know it's supposed to be a parabola. But how do you get there from this?
You solve for...
Can you write this in the form y equals f of x? Or it doesn't even have to be a function. Y relation with x.
Solve for t and x and then plug it in for y?
I love it. The most basic way to do it, and you do this all the time unless it's bad to do it. Sometimes you can't solve for t, so you got to figure out some other way. You take this equation and you solve for t, so you get
1 minus x.
1 minus x, and then you plug it in. Does anybody else see something interesting? I mean, that'll work. That'll work all day long. Right? If nobody else sees something interesting, we'll do it this way. Yeah, how does y factor?
T minus 1.
Squared, which is the same as 1 minus t squared. Do you guys realize that? Do you guys realize that? Is that cool? What's 3 minus 7 squared? 16, which is the same as 7 minus 3 squared, right? It's sort of like taking an absolute value. It doesn't matter which order you put them in because the square is going to kill the negative. It's a very interesting thing to realize.
Yes.
Okay, good. All right. So there's a much quicker way to do this. Y equals, what's 1 minus t? What's 1 minus t?
X.
X. Y equals x squared, which is going along with the picture we've got, right? Now, if you do this, it will, if you plug 1 minus x in for t and simplify that, it will get you there. But the first thing I look for is there any immediate connection that I can see? If there's trig functions, is there some trig identity that connects them? Something like that. Okay, cool. I like it. So let me do this. Let me give you, sure. This has got a little more information on it, but I want you to do the first problem on this. And then we'll look at some more interesting cases, and then we'll call it a day. If I say that phrase, it normally picks people up a little bit. Like light at the end of the tunnel. I can do this. That's it.
I don't know where you got the y equal x squared.
So y equals this, is that cool?
Okay.
And then 1 minus t is x. So you can see connection directly between them. You don't have to do as much work. But, you know, solving for t and plugging it in, that will almost always work if you can solve for t. Cool.
Can the Cartesian be in terms of x equals y?
Totally. And often you'll get Cartesian that you can't solve for x or y.
Right.
Yeah. Good. All right. How are we doing out there? guys get this?
Yep.
All right, and then when you graph this, let's see.
Yep.
X, you got to go up to 4, down to negative 4. Y, got to go down to negative 5.
Up to
3. Negative 4, negative 5. 0, negative 3. Negative 2, negative 1. You can do it, Jeff. Can you? Negative 4, 1. And then 0, 3. And something about this, you have to connect the dots in the order in which they were created. I always get somebody who does this and then they just start connecting, whatever way they want to. I see an elephant. No, so you have to. And another thing is, do I connect them with straight lines?
I was going to ask that.
No.
One of the equations is a cubic. It's not going to be a straight line, right?
No.
So you want to connect these with, and most likely it's going to be something like this. Right? Cool. I like it. Bless you. And then how do you eliminate the parameter?
Solve for t and y.
Good. So you know t is y plus 3 over 2.
Yeah.
And then you just plug it into x. Y plus 3 over 2. Please, dear God, you can stop here. Minus 3 times y plus 3 over 2 squared. Which is, if you wanted to, pull out 2 of those. That's 3 years. Which makes sense. I mean, this is a function. This is not a function of x, but if you look at it this way, it is a function. It does pass the vertical line test if you turn it.
Right.
So it is a function of y. X is a function of y. Cool. Which makes sense because x is a function of y. Kick ass, right? So there will be situations. For example, if you have your calculator with you, how many of you guys have never done any of what I'm doing right now? Is this true for anybody? Again. The educational system has failed you. Does it make sense so far? Good. All right, good. Here's how you do this in your calculator. So if you turn on this, so they can see it, Jeff. If one of them will work. Okay. So let me show you how to make this show up. Go to mode. See down here, this should be like func. You got parametric, polar, and even sequential. Ooh. So if you go over to parametric PAR, select that one. If you go to y equals, it should look like this now. So we'll play around with those in a second. Let's put this, what we just did. Where's your equations, Jeff? I didn't
T
put it up.
cubed minus 3t squared.
Like, what is happening back there?
And 2t minus 3.
I was going to say share. Okay. And before you go to graph, go to your window, and what did this problem say? Yeah, negative 1 to 3. And I also know that it's going to be, it should fit in negative 6 to 6, so that's fine. I'm just going to leave it like that. I can change my x and y for my xy plane.
The t step, are we going to change to 1 or we're going to use decimal value?
Now, here, I'll show you. Watch, wait. So we'll use the default here. If I graph it, it looks decent, right?
Yeah.
But see how it doesn't quite connect here? So if I make my t-step smaller, like 0.05, it's going to make it a lot finer. And it does connect, right? Now, everybody kind of with me? So that's sort of a resolution. It's actually how many entries in its table are there for the graph, for the calculator. So if I make it something really silly, if I make it 1, watch what happens.
Square points.
Bah, bah, bah. If I make it, let me see, if I make it 2, this is going to be horrible. Bah. So you didn't get enough points to resolve where, and it just connects the points it got, right? So
this one we use is going to be the most precise.
0.1 is decent. Well, you know, there's a caveat between if you make it too good, then it goes like it goes like this. The computer here is pretty good, but if I make it 0.001,
We're playing Snake.
Stop. Oh, thank God. All right. I got to restart the program now. Oh, there you go. All right, so just to remind you guys, if you want the T to show up, you got to go to Mode, PAR. Now let's play around with this a little bit. Some of you guys should be at the point where you're okay with playing around with this. If I put, let's just put, well, I'm going to put this, well, I was playing around with it a second ago. 3 cosine. Well, actually, what? First off, if I just make these the same, 3, 3, and I make this the same, what picture should this be?
Circle.
No way. Now, of course, I've got, Jeff, you have to, Jeff. I forgot.
T is slow.
I forgot. Go away. Go away. Go away so I can bring you again. Okay. Eventually it's going to be like, I'm not going to open for you, man. All right, let's change that. Now, what do you think I want my T min and T max to be, maybe? Maybe 0 to 2 pi to start with, right? And especially because my trig functions are of T, so the period, both of the periods of my trig functions are 2 pi, so it makes sense. They should go through all their values.
Yep.
So we graph this bad boy. It looks like Stewie's head, but because this is not square, of course, you know, circles will look like footballs.
Can't you zoom square?
Yeah, you could. Yeah, exactly. You can zoom square. You can set it to the right dimension so it corrects for it.
But this is because of the units, isn't it?
It's because it's not a square screen. So there is a zoom square that sets it so that it approximates a square screen. You look at your window, that's what you have to do to it. All right.
Yeah.
So what if I play with this a little bit? What if I make this 2t? What does that do?
Gonna be an oval.
So that means, what happens to the period if I do that? What happens to the period for the x trig function?
It's twice as fast.
Yeah, because the period now becomes half as much. Now the period is pi, right? So it's going quicker on the x than it used to. So I want you to make a circle. My x rate has got to be perfect so that, and my y rate, so that together they make this circle. So now my x is going too fast. So let's see. Some of you guys might realize, but let's see what happens. Poor little thing. Isn't that neat? Alright, I don't know if you guys are understanding what happened. Does that kind of make sense? The x went too fast. So the y was still going up like, okay, well, I think we're going to be here. And the x was like, no, I'm over here already. So it makes this figure 8, makes this hourglass. So
if you switched it, would it be like an infinity symbol?
exactly, 11. So if we put a 2 in there. No, Jeff, get out.
14.
Yeah, we could do that. So now it'll be, well, that's more interesting. And the reason that is because notice how I have my trig function set up. So what happens if I switch them back cosine and sine now? Now I do get that.
Infinite.
All right. And then, I mean, from there you can play around with, well, what if that was a 4? And what if I did put a 3 into this one? And of course, now I have to actually change my, let's see if we can make it. Oh, there it goes. Almost. If I make my T max 4 pi instead, just to make sure that I get everywhere I want to go. Okay, good. And then it starts to retrace itself. Cool. I like it. I like it.
So what would happen if you went half T?
All right, see, this is what I'm talking about. This is what, you know, when I was a little kid, we didn't have TI. You gave me just a normal calculator, and that would keep me busy for an hour. I don't know. I don't remember what I did, but I would sit in the corner, and I would just play with it. And I'm not sure. And my mom was like, is that all it takes? Oh, thank God. So, just give a freaking calculator. All right. So, but now, holy shit, if these existed when I was a little kid, dude. So I love it. That's exactly the attitude you want to have. What if this? What if this? What if this? What the hell? Who gives a shit? This is not going to blow up. At worst, they'll say syntax error, right? So you can totally do whatever the hell you want to, and then see what happens, and then go, well, why did that happen? It's beautiful. Tears. Right? And not just because you're playing around with a freaking calculator, because you're wondering about how does the math affect the image. Changing the equation, how does it affect the image? Why does it affect the image that way? Neat shit. Now watch this. Watch. You ready? Let's go back to basics here. What's this going to be the picture of? What's different from it being a circle?
Cosine's going.
Now these are not equal, right? So this will be officially an ellipse. Of course, I think it's still in square, so that's nice. Now watch, this gets interesting now. You ready?
It's retracing.
Of course, yeah, I have my t going through 4 pi instead of 2 pi. This is where it gets really cool. You ready? What if I add t? That means my x is constantly getting bigger, right? And of course, it's t plus a little trig function sign. So what's going to happen is it's going to be doing like this. Let's see what happens. Yeah. Isn't that cool? It's freaking cool.
Roller coaster type.
Right? And if I zoom out a little bit. Let's see, and if we put on this one minus t,
It's gonna go down.
now it's going to move diagonally.
Oh, shoot.
See, now we're talking some cool shit. And then, what you guys do if you get to 281, if you're not going to, it's just too bad for you. But you'll start to do stuff like that in 3 dimensions, where you have a circle in the xy plane, but then you say z is t. So then it's making a circle and going up like that, right?
It makes a sphere.
Dude, not a sphere, it's just like a coil. A spring. Yeah. A sphere is where I got to control the radius and it grows and then shrinks as you go up. Yeah.
So you could probably like find an equation to like write your name or something.
Of course, dude. Yes.
You know yours?
Is parametric?
There's an equation that you can put in that will create a butterfly on your calculator. It's called the butterfly curve. It's got a Wikipedia entry. So if you want to look up that equation, I did that for my 176 class, but you guys can look it up.
Is parametrics the one that gives you the saddle curve in 3 dimensions?
You don't need parametric to do that.
Okay.
Yeah. And again, a lot of the stuff, I can make a parabola using parametric equations I use, right? And I want you to realize something. It's something like that. You could put it in parametric form, and you can see some things easier in parametric form. Does that sort of make sense? I mean, that's another reason the forms
You couldn't do a
exist.
circle in function form because it doesn't pass the line.
Yeah, you have to do it in 2 parts. Exactly. Okay. Oh shit! What was I about to do? Did I give any?
Saddle equation.
No. Shit. Something said made me think of something important and I forgot. Oh, here it is. All right. If I give you this equation, we saw earlier one way to write this parametrically. What's another way to write this parametrically? Here, I'll start off.
X equals square root of y.
There. That's the most boring one, right? That's what I would call the trivial solution to this. This is one way to do it. What's another way to do it?
The one we had earlier.
Yeah, the one we had earlier. So x equals
T plus.
square root of t,
Yeah.
and then y would be t. Now think about that. Now, here's the reason I want to talk about this. One, there's 2 reasons. One is just to make you realize you basically have an infinite range of ways to define something parametrically. But your choice has consequences. Right? Nobody has to die or anything, right? Push the button. No, I don't push the button. This still becomes this. I'm sorry, becomes this. True?
Yes.
But what's that choice of square root of t? Can I get, what part of this picture will I not get? Well, can x not be?
Yeah.
X can't be negative. So this will only give me this part of it, right? So your choice of function to use in the parametric equations will affect what your graph looks like, or what part of the graph you get. What if I did, what's another way using trig functions?
Trig functions.
Totally. Trig functions. So it could be something like, if you say y, x is cosine of t, what would y have to be? To be y equals x squared? Cosine squared t, thank you. The minute I do that, what's the limits on the outputs of cosine? Come on now.
Limits?
Limits on the outputs of cosine. What's the range of cosine? Yes, so then you'll only get this part of your parabola. Do you see what I'm saying? So you have a lot of flexibility in terms of how to define parametric equations for a given rectangular coordinate system equation. Holy shit! Let me say that again. You have a lot of flexibility in how to define parametric equations for a given equation. Cool?
Yes.
But your choice in functions will alter what part of the graph you get. Because they have their own domains and ranges and so forth, right? Okay, cool, I like it. And of course, this has more to do with us as we move forward into the calculus of parametric equations, because our choice of function to use will go quicker or slower than some other choice might. And we're going to be talking about derivatives of these parametric equations, right? So you guys can see on the handout how those work. They work actually exactly the way you would hope they would. You would hope that dy over dx is dy dt over dx dt, and your prayer has been answered. It's true. It's like, thank God, it's the simple, straightforward, what I hope it would be. If you guys don't realize that, you don't have to. It's still as easy as you could hope. There's one last thing I want to say. Oh, there are some really good examples in the book, like on page 639. If you don't have the book with you, for example, let me see if I can do this real quick. Oh, wow. That looks really gross. Sorry. Oh, well, I don't know if that would change anything. I got to zoom in a little bit, but oh well. Screw it. I was trying to make the picture on page 639. The range is, the T max and T min probably has to be something different. You got all kinds of nifty starting off, jumping off points on page 639. But then if you just Google stuff like the butterfly curve, I mean, and look at the Wikipedia entry, and they have entries, yeah, you got it. The equation is not simple. It's kind of long. I certainly don't have it memorized. It's got e's in it and signs in it and stuff. It's all over the place. But this stuff is so cool. I don't know if you guys can pick up that for me. Yeah, in the homework, for example, and very often these will have interesting names, like number 43 in the homework, you got a curve called the Witch of Maria Agnesi. So you know it's got some kind of a backstory to it. Sounds like it was in a Monty Python movie, I don't know. This sounds like it's from a Monty Python movie too. Swallowtail catastrophe curve, and that's beautiful. The swallowtail catastrophe curve. I mean, come on. That's number 48. I'm not making it up. Right? Kicks so much ass.
You should have made for it.
What?
You should.
Sure, man.
Like the water reform.
The water. Waller waterfall. Sounds like Wonderwall. All right.
So are the problems in the book just testing it out in your calculator?
No. So what the problems in the book do, they of course make you do this. They make you. Some of the problems are going to give you this, and you have to come up with parametric equations for it. They're going to ask you to graph it, so you got to make a TXY table, right? TXY table. They're going to give you images, graphs, and they're going to say pick which one relates to the function. And for that one, you've seen that kind of problem a million times throughout your math career.
Right.
So you can do it like, does it go through the right point that this one goes through? Stuff like that. Does it look? If it's defined based on polynomials versus defined based on trig functions like cosine and sine, what's the main difference going to be? How do I say this? See these arrows? All right, they're unbounded, right? They're just going to keep going. If I define x and y based on cosine of something and sine of something, then the image is going to have to be contained. Because cosine and sine will start to repeat. They only go out to 1 and -1. Do you guys see what I'm saying? So on these connect the function with its graph questions, you say, okay, that function only has trig functions, the cosine and sine. It's got to be some contained image. But the ones that go like this, they're kind of easy because they're going to be some kind of plus t like we did earlier. They're definitely not going to be only trig functions. They're going to have something on the outside of them. Or minus t, or, yeah, exactly. I like it.
And sine and cosine can be expanded by the 4.
Yeah, that just changed the amplitude. Yeah. That's why I was putting 5s on this, is because my window was bigger and I was lazy, didn't want to change my window. I didn't make it big enough. Oh, and for the person asking about your name, number 35 and 36, the 35 is a happy face. And number 36 is a cart, I guess. Like in high school calculus, they very often have little, what do you call it? Contests where you try to create parametric equations that give certain pictures, like Homer Simpson or something. Yeah.
Did you show how to get to the calculator?
Yeah, go to mode, and then select the PAR for parametric. Yeah, don't go funky. Go par.
You want to be up to par.
Up to par. I'm glad somebody else came up with it. It's really thanks to my name. All right, guys. That's perfect.
On Friday for the makeup, is this not like accurate?
Say again? Oh, I haven't gotten yours yet.
Yeah, so
I haven't been to the mailbox today yet. It wasn't in my mailbox yesterday, but you took it on Friday, right?
Friday, like
So they must have put it in the mailbox
okay.
last night.
Cool.